really fundamental today, a core piece of how the universe actually works.
Yeah, absolutely.
Something so, woven into reality we barely think about it, the nature of light. Specifically, we're talking about the mass of the photon.
And we've got some fascinating sources here. We're diving into the theory, the mind-bending experiments, and even thinking about the what-ifs.
Right.
Our mission today is really to unpack what this research tells us. Why do physicists think the photon is massless? How do they even test that? And, why does it matter so much?
Exactly. We're going straight to the heart of it. So let's maybe start with the particle itself, the photon. What is it?
Okay, so the photon, you often see it written as gamma. It's the basic unit, the quantum of the electromagnetic field.
Like the smallest possible packet of light.
Exactly. Smallest packet of light, radio waves, X-rays, all that stuff. It's the particle that carries the electromagnetic force. It's pretty fundamental in the standard model.
And the theory, the standard model view, is really quite definite about its mass, isn't it?
It is. Very definite. The standard model says the photon has exactly 0 rest mass. Not just tiny, but precisely 0. It's like built into the foundations of the theory.
It's not just an assumption, it's a core prediction.
Absolutely. And the sources link this right into quantum electrodynamics, QED.
The quantum theory of light and electricity.
Right. QED calls the photon a gauge boson. And that's tied to something called U1 gauge symmetry. Now, gauge symmetry sounds technical, I know.
Yeah, a bit.
But the key thing the sources emphasize is that this symmetry is incredibly important. It dictates how the force behaves.
Because if the photon did have mass, even a tiny bit, that symmetry would be broken.
Exactly. It breaks. And
All
the
right.
consequence is huge. If that U1 symmetry isn't perfect because of a photon mass, then the electromagnetic force changes character completely. It stops being a long-range force.
It becomes short range.
Yeah, it would drop off really quickly with distance, like the weak nuclear force, essentially.
Whoa, hang on. So the fact that we can see stars billions of light years away, or even just, use a compass that relies on the photon having 0 mass.
That's precisely it. The infinite range of electromagnetism, the reason light travels across the cosmos and magnetic fields stretch out, is a direct consequence of its carrier particle, the photon, being massless. It connects this deep theoretical symmetry to just, how the universe looks.
That's incredible. Okay, and this masslessness thing, it also connects to the speed of light, CC.
Oh, absolutely.
Yeah.
It's a direct result. Because theory says the photon is massless, Einstein's special relativity demands it must travel at the speed of light, c, in a vacuum. No other speed is possible for it.
Right, that famous equation E squared equals MC squared plus PC squared.
EPC plus PC.
That's calling in me equals 0 for the mass.
The whole MC term just vanishes. You're left with E port and PC cool, or simply EPC. Energy equals momentum times the speed of light.
And that relationship only works for massless things moving at c.
Exactly. That's the mathematical signature of a massless particle traveling at light speed.
Yeah.
Anything with mass, even the tiny bit, could never quite reach c. It would take infinite energy.
Yeah.
So the fact that light travels at c is, strong evidence for it being massless.
Okay, so the theory side seems crystal clear. 0 mass. But experimentally, proving something is exactly 0 seems, impossible. How do you measure 0?
You can't really, not definitively prove absolute 0. What physicists do, and our sources detail this really well, is they set limits. They perform experiments designed to detect any effect that would happen if the photon did have mass, and then they see how small that effect could possibly be.
So they're constantly shrinking the box, saying if it has mass, it has to be smaller than this.
Precisely. They've had increasingly stringent upper limits on what the mass could be.
And where are we now? What's the current record for that upper limit? How small are we talking?
The current experimental upper limit is...
Yeah.
It's almost hard to state how small it is. It's less than 1 × 10 to the minus 18 electron volts per c squared. So 10 EVC.
Okay, 10 to the minus 18. That sounds tiny. Can you, put that in perspective compared to something we know?
Yeah, let's compare to an electron. An electron's mass is about 500,000 EVCC, roughly 5 times 10 UVCC whole.
Sure.
So the upper limit on the photon's mass is, wait for it, more than 10 to the power of 23 times smaller than the mass of 1 electron.
Wow. That's basically 0 for all intents and purposes, isn't it?
It's incredibly close. So close, it's difficult to imagine it not being 0. It doesn't mathematically prove 0, but it's phenomenally strong evidence supporting the theory. It means if there is a mass, it's almost unimaginably tiny.
That kind of precision is just staggering. How do scientists even design experiments to look for something that subtle? What are the methods?
It takes some really ingenious approaches, often looking for tiny deviations from known physics or using cosmic scales. One way is testing Coulomb's law really, really precisely.
The inverse square law for electric force.
Exactly. If the photon had mass, the force wouldn't be a perfect 1 over r squared. It would fall off slightly faster, exponentially, described by Yukawa potential. So super precise measurements of electric fields can look for that tiny extra fall off.
Like checking if the force gets slightly weaker than expected at long distances.
Kind of, yeah. Or looking for tiny deviations in the shape of the field. Another way is to go big. Really big.
Like astronomical scales.
Yep. Think about large-scale magnetic fields, planets, stars, even entire galaxies. These fields stretch over immense distances.
Right.
If the photon carrying that force had mass, the field wouldn't be able to reach so far. It would essentially get screened or fade out much more quickly. The very fact that we observe huge galactic magnetic fields spanning thousands, even tens of thousands of light years, tells us the photon must be massless, or extremely close to it.
Because otherwise those fields just couldn't exist on that scale.
Correct. The range would be limited by the photon's mass. Seeing those fields puts incredibly tight bounds on how massive the photon could possibly be.
And this is where looking at light from very distant events comes in. The cosmic laboratory idea.
Yes, that's one of the most powerful techniques, as the sources highlight. Here's the thing. If photons had mass, their speed wouldn't be constant c. It would actually depend slightly on their energy or frequency.
Wait, so blue light would travel at a different speed than red light in a
Well,
vacuum?
In principle, yes.
Well,
Higher energy photons, like gamma rays or blue light, would travel just a tiny bit faster than lower energy ones, like radio waves or red light.
okay. So if you have something really far away, like a supernova or a gamma ray burst.
Exactly. An event that emits light across a huge range of energies, all at essentially the same moment, if it's billions of light years away.
Then over that massive distance, even a tiny speed difference would add up. The high energy light should arrive first.
Precisely. You'd expect the gamma rays to get here maybe seconds, minutes, or even days before the radio waves, depending on the mass and the distance.
But do we see that?
We don't. When we observe these distant bursts, the light across different energies arrives remarkably close together, often within seconds, after traveling for billions of years. That near-perfect simultaneous arrival puts absolutely incredible constraints on any possible photon mass. The universe itself becomes the precision instrument.
That's amazing. Using the sheer scale of the cosmos to amplify a tiny potential difference. So clever.
It really is. And the sources mention other things too. Super precise tests of Ampere's law, looking at magnetic fields, and even some quantum effects like the Aronoff-Bohm effect. It's like attacking the problem from every conceivable angle.
Okay, so let's play that what-if game the source material suggests. What if, against all this evidence, some future experiment actually found definitive proof of a tiny non-zero photon mass? What would break?
Oh, it would be revolutionary. A genuine paradigm shift. First off, Maxwell's equations, the bedrock of classical electromagnetism, would be wrong. Or, well, incomplete. They'd need to be replaced by something called the Proctor equations.
And that beautiful gauge symmetry.
Gone, broken, fundamentally. Which means the electromagnetic force would, as we discussed, become short range.
Which would change everything.
It would change so much. How atoms bind beyond certain distances, how plasma behaves, how galactic magnetic fields form and persist. The universe would operate under subtly different rules. Depending on how big that tiny mass was, the effects could range from barely detectable to quite significant on cosmic scales.
And the speed of light wouldn't be constant anymore.
Not a universal constant for all light, no.
Yeah.
The speed c would likely remain the ultimate speed limit, but photons of different energies would travel at slightly different speeds below c, even in a vacuum. You'd get this dispersion effect where light separates like in a prism just by traveling through empty space. Our view of distant galaxies would be subtly smeared out in time.
Any other weird effects? Like, could photons decay?
Theoretically, if they had mass, they could potentially decay into lighter particles, like maybe neutrinos. But given how long photons demonstrably last, traveling billions of years, the limits on that decay rate are already incredibly strict, even assuming a mass. It's very unlikely, but technically possible in some models, and there could be other subtle cosmological consequences too.
Okay, so wrapping up this deep dive on photon mass, what are the absolute key takeaways we should hold on to from the sources?
I think there are two main pillars. First, the theory. The standard model, based on fundamental principles like gauge symmetry, strongly predicts the photon's rest mass is exactly zero. This isn't just a guess. It's needed for electromagnetism to be long-range and for light to travel at sea.
Pillar 1, theory says 0.
Right. Pillar 2, experiment. While we can't prove exact zero, the experimental upper limits are now astonishingly small, less than 10 your EVC.
So small, it's hard to wrap your head around.
Exactly. And these limits come from incredibly clever experiments, from tabletop precision tests to using the entire universe as a detector. The experimental data overwhelmingly supports the theory. It's one of the best tested zeros in physics.
It's a fantastic illustration of theory predicting something profound, an experiment pushing technology and ingenuity to the absolute edge to verify it.
Couldn't have said it better myself. And, the search isn't over. Physicists are always looking for new ways to push those limits even further down, constantly checking that zero.
So as we finish up, just take a moment to think about that. The sheer effort and brilliance needed to measure something that might be nothing, and to confirm it's closer to nothing than we almost imagined possible. And then ponder what it would truly mean if someday that tiny sliver of possibility, that non-zero mass, turned out to be real. What hidden physics, what new understanding of reality might that single infinitesimal number suddenly unlock? What foundations would we have to rebuild?